Okay. I am in for another stream for the day. First one of the week, feeling pretty good. I have a bit of an actual design project in mind. If you look here, you can actually see part of it already. But I'm gonna design dumbbells that I can make at the metal shop. Yeah, that's pretty much all there is to it. Nothing too crazy going on. All right. So with all that, let me just make sure things are working okay. I have the visual appearance of working okay. And I have my coffee. I think we're good to go. Let's pop the scene here. Okay, things are looking fine. Okay, so I'm going to start off actually by let's see here. Let's try to clean up the view a little bit here. Get things working in a nice, concise view. Alright, so what I've got is, I actually started working on this morning a little bit. I've got, this should be working. This is a file, I don't need that open, I need this. This right here. This is my local copy. There we go. Hey Emerson, how's it going? Hope you're doing well today. There we go. Okay, we've got this nice bit of design actually working, which is pretty cool. Things are a little slow with the rotate, but that is not too surprising. Yeah, you're fine. What about me? I'm doing well today. I'm pretty happy to be working on some design work here. It's nice because the code I'm working on is actually letting me do some pretty cool things with dynamic changes and stuff like that. It's cool. I'm excited that it actually is working. So that feels nice. Otherwise, I'm just in a good mood, which is always helpful, of course. And yeah, just having a good time. Having a good time. Okay, if we zip this up here. Zoop. Yeah. So what I want to do is adjust how this actually looks, because it's a little cluttered, it's a little messy, not immediately clear what is going on. And you've got some slow rendering as well. So I don't know how exactly I'm going to change that. The other thing is, I want the users, this is just a this is a design for dumbbells, like for weightlifting. I want to have it so that the user can provide basically the desired mass of the piece, and then basically everything else derives automatically from that. So I have to kind of adjust how this is done. I also have it in it's done in a messy way here. I've just got a bunch of global variables up here, which is not necessarily the smartest approach, but that's something I can work on. I think that can be fine. Yeah. Actually, I'm gonna lost my train of thought. Okay, so there's a few things I don't actually need to provide as atoms. What's the right thing for me to do next? That's my question. That's the question I have for myself, and I don't know the answer. Let's see. Oh yes, well, so one thing I do know, since some of these are going to be hard-coded anyway, it does make sense to start these at the values I know will exist. This looks like a TIE fighter, almost. Okay, so first of all, there's an issue here. I don't know why that's spread wrong, so maybe I'll start there. I'll just get the I'll get the model working okay. So first of all, what I can do is hide this, shrink things down a little bit here. Okay, so we have one view. That's okay. That looks pretty good. Let's do one more thing here. If we change the view rotation here to 135, then the default rotation lets us visually check this offset here, and now I can go ahead and work on that. Let's also shrink this a little bit more. Have a look at this here. Okay, so basically what I'm doing is working on a scratch pad proto design document thing here. Does that make any sense? I don't know. I'm gonna split this and just start adding little labels here. Globals, parts. So we've got a hex plate, a tube, plate and handle. I should actually move that. Yeah, that makes sense. Here I've got property calculations. Does that make sense? Yeah, kinda. That's fine for now. And then here we've got base views, right? Yeah, and part views. Okay, and now here we've got assembly, and here we've got assembly view. Oh, this is a mistake. Gotta split. Oop. Come on. One day I'll get this right. Okay. Split. Oh, I put the title in the wrong line there. That's okay. Paste that. Nope, I also pasted it in the wrong spot. Boy, oh boy, off to a rocky start. That's fine though. Okay, there we go. Assembly view. Total mass actually gets calculated earlier. which is something I can put up here. That should work fine. Oh, that's not entirely true though, actually. I've got a simple solution here. Actually, that should be fine. That's totally fine. Assembly view, and here we've got the what I'm calling the doc view. Yeah, that's fine. Okay, let's see that these sections make sense. Globals, parts. So what I'd kind of like to do is move it like this. Globals, parts, assembly, property calculations, part views, assembly views, and then the doc. So that should be okay. Let's see that it actually does work. And in fact, just as a check, I'm going to go ahead and recompile from the start and see how that goes. It should be fine, but I just want to see if maybe there's some state that something got messed up as I was developing. But this should be fine as a start. I hope. Okay, so that's a good start. So the whole goal of this is to build, call it a little app that gives me the exact measurements for the parts I have to cut and then weld together to get a certain weight from the thing, from the piece. I can restrict, so zoom is just a display thing, not a big deal. Number of plates, if I shrink it down, things speed up a little bit because there's less to render, of course, which is nice. One other thing that I'm gonna do just to speed up rendering a bit here, I have a work in progress curve render function, and what it does is subdivide curves into 15 segments, and the problem there is most of the segments in this drawing are straight segments except for the tube. So there's a lot of segments that are needlessly are subdivided by a large amount here. So I'm going to try and see how clean this looks. If I just reduce the subdivisions, it should shrink the size of the SVG being rendered. But we'll have to see if that actually makes sense. I also will need to refresh a few things. Oh, did this even save? I did save it. This isn't gonna be done yet. Let's go to parts. No, let's just change here. I want to change the assembly view size. Let's make it 400 by 250. Pardon me, doesn't need to be that big. Okay. Okay, and now let's refresh one more time, because I think now it should incorporate the reduction. Yeah. So what I've just done there is only, you can only tell this tube is technically a circle. 7's a little too low though. But it's been subdivided into straight segments. And the way I've got the curve renderer working is it subdivides every single curve evenly, even if it's a straight line. So it just adds technically unnecessary data into it. So just gonna compromise with that. Maybe 10 will be good enough. It just isn't a perfect solution yet, but I do need to get something visible, get some visual feedback for this work, which is nice. Okay, let's see here. Let's get the zoom level to 100. There. Okay. Save this just to make sure change is good. Refresh that. This width. That's good. That's fine. Okay. So, what can I do next? Okay. So what I know I can do, or should do, is adjust here. Instead of having a dock, so let me do this. I'm gonna split parameter views. I guess I'd call it that. What I'm doing is building controllable parameters with these here. And to do that, I'll start by what I can do define parameters as an empty function. Yeah, I think that's pretty reasonable. We'll start by doing this. We'll cut and paste. Just get those out of there into here, into their own thing. And remove the ones that I know I don't need. So, well, actually, first of all, let me just collect them all into one spot. So this one too. Okay. And then, so there's parameter view, and then there's also a property view, I guess. by properties, I mean more information, not something you can change per se. Actually, let me get away from that for now. Yeah, I'll cut this one here, total mass. Just get rid of it. Okay, so that should really pare down the view of this to basically nothing. Let's also close off parameters there. Okay, so now I can't control it because I don't have any UI components rendered into the scene, so that won't move. So if I wanted to put it in, parameters, that should work. Okay, it does. There we go. So parameters, view controls would be, yeah, that's fine. I'm not designing these in the most clever way right now, but for the sake of getting this sort of minimum viable prototype out, it's fine. There's definitely smarter ways that you can kind of wrap the UI components together, maybe even build macros that automatically instrument whatever model you send to it without you having to specify things up front, but that's all ideas for another day. Getting some nice working example is important, even if it's not perfect. Okay, so the view controls, I won't do it in a span, I'll just do it in a div for now, it's fine. View controls, okay, is the rotate and the zoom. Yeah, right. Oops. Close the div, close that. So now those two should disappear. Yep. Material density won't change, so I can actually get rid of it. Yes. Plate T. Plate R, and number of plates actually won't change according to this either. It'll change according to a formula that I have to develop, but instead I'll have something called desired mass. Yeah, that's a good idea. Slider, no. Input, desired mass, and let's start at, oh no, let's not make it a text input. We'll make it a slider for now, because for the time being that's fine. It's not perfect, but minimum 5 pounds. Let's say the maximum, let's assume we can go up to 100 pounds, and we'll go in increments of what? What's a good pound increment? 2.5? That seems reasonable to me. And we'll do display it with the span like that. Close the div, close that, close parameters. So this here, desired mass is the plate mass G desired mass pounds. For now, I'm just going to, oh, and this will give a warning because this doesn't exist. Desired mass has to be added to the list of globals here, which, by the way, I probably want to add into a single thing called state and treat all of these as keys to a map or something. That I think is cleaner. I just was doing this because I was lazy when I was working on this morning. I was just doing the quick and easy thing. The desired mass starting point is 5 pounds. It's a good default. And the way that the slider works, it won't allow you to put in incorrect values. It'll constrain that automatically. In an ideal world, you would have, say, in the instrumentation process, right? If you have a model and you've got all the parameters you want to control, you have a macro or something that generates a spec for it, or you use a spec to define. You could write a spec and use the spec to auto-generate the parameter controls or something. There's almost certainly a cool way to do it, clever way. I just have to think about it, because this is the first go at making something like this that I'm working on anyway, so it's just exploratory. But it is exciting. At least to me, it's exciting. It's just called slider. Desired mass 5 pounds. This is not attached to anything, so it won't change anything, but you can control it there. 5, 7.5, 10, 12.5. Up to 100 pounds. Maybe up to 80 is probably. Probably we won't go higher. You know what? I'll leave it at 100, and they'll see what the design looks like. Because it's gonna look weird at a certain size, so we will work with that. There's gotta be another. I have to set one more thing actually. I need to kind of lock one more parameter in place. So plate T, plate R needs clarification, but I can do that later. This here is, oh no, plate R is, oh no, we're good. Okay, this should be enough information to work with. Oh, and now of course I want to add back in the view controls. So what I do here, I can do it under here. I can do view controls under that. Nice. Okay. So there's desired mass. I do want to show actual mass. No, I don't need to show that yet, because what I'm going to do okay. So let me think about this. I need here split. Call this model logic. Okay, so let me kind of write this out for myself here. So user locks desired mass calculate user locks desired mass. The user locks max hex radius with those locked, all of the other things are presumed locked as well. So the handle width is fixed, is a fixed value. The plate calculate mass of handle, easy. Calculate mass of one plate, one max sized plate. Then for let's see, calculate number of plates closest that result in mass closest to desired without going over. Remaining mass is added by calculating plate size remaining mass is added by calculating size of smaller remainder plates. Okay, so what does any of that mean? What I can do is create, so let me do something here where I define this is hard for me to, this shouldn't be that hard, but my brain is not latching on to the obvious solutions yet. First thing I want is to let's make a function here, calculate hex r given some desired mass and for right now we're gonna no, let's do it like this. So calculate hex radius. See, this actually note to self, this may be a great time to learn learn to learn. What is that called? There's a library. What is the library called? Clojure script. I totally forget what it's called. It's a type of programming. It's declarative programming. Okay. Shoot, what is it? Cond P is not the right thing to search either. Clojure declarative programming. There's a name for this. Oh, core.logic, I think it is. Let's see here. Clojure core.logic. Yeah, this is the to learn logic programming. The reason for that is you can write functions in such a way that you can kind of solve, like you can write a function that takes 3 variables. You can give it any two, and it will solve the third, or whatever. So I don't understand it well enough yet. I've done some tutorials before, but my comfort level is low, so I'm not going to use it right now. I'm just going to kind of hack together something that'll work for my purposes here. But almost certainly there's some use to be had with core.logic. So let me core.logic. Let's go ahead and that's a note to myself. That's for another time though. Okay. So calculate the hex radius given the what do I need to know? I've locked in the plate thickness, T. R is not known. The desired mass is known. And of course, to get mass, you do need density as well, right? So you can calculate the volume of something, multiply the volume by the density, and that'll get you the mass. So for some given this is not quite maybe I do need I suppose I could do like an iterator and just go until a minimum difference is reached, and that'll get me close to desired value. I'm gonna get myself a coffee for a second. I will be right back. If I go here, BRB. I won't be too long. Just wanna get the coffee. Okay, where was I here? Let's see what I can come up with. I am back. Okay, so theoretically, what I can do oh, I also, actually, while I'm looking at this, I do also need R, thickness, mass, density. Yeah, that makes sense. R, max R, so you can run things from for a range. You also know I can put in min R as a parameter in this case. That should be good. Oh, this might be a little easier than I thought if I kind of cheat the system a little bit. So what I want to do is make a higher order function. So let f be some function which is partial well, let's build out this function. This function I want to return, I want to take in as an argument a radius, and I want it to return the mass of the plate of that radius. So what I need to do is have a quick look at how I did this. Parts. This might have been a mistake here. Let's change this to be plate, where you take in a radius like this. Okay, so that's the plate function, and that does mean here in assembly I have to change this a little bit to be let plate be plate at g dash plate r, and then everything else should still be fine. Let's see if that's true. Something's wrong. Oh, okay, well, that's gonna have to be fine. Let me just check. Okay, so it does work. It seems to, anyway. Good, things are still responding to it. Desired mass, of course, makes no difference. Plate thickness does indeed change the plate thickness. There's something wrong with this side which I forgot to fix, which I'll have to do at some point, but it's not right now. Zoom, rotate, still fine. Okay, we're good. So with that, I have a function that's called plate. So let's do let f be the function plate mass. No. Geez, I'm already forgetting what I have to do here. So the function plate takes, that's not the view, I need this here. The function plate, right, takes a radius. Okay, that's all I need to know. plate volume of plate given some radius, right? That's the function. Here I can do this volume multiplied by the density. Okay, that's the function. And then all I need to do here yeah, let's try that. So then right, let's take min of, apply min of, oh, this looks ugly, of map f onto range from min r to max r with some step size. Okay, let's see if this actually works for me. How can I test this? Oh, I think I understand. Okay, so it also shouldn't be min, it should actually be this is actually not correct either. It has to be map the result. You have to take minimum of math/absolute of subtract the function minus desired mass. So now if you do the min of that, you should get oh shoot, it's got to be, well, that's also wrong, right? Because I don't want the result of that, I want the radius that provided that result. So let's rethink this just a little bit. Ours is range min r max r some step value, which I'll hard code here, right? So that's the r's. Oh, let's also do into vector start there. So then for oh, no. We'll do it like this. Okay, the r's are for r in range min r max r step. For each of those, you have to do this calculation did something wrong. Well, math abs minus f mass. I don't think you need to do math abs, right? Shouldn't matter. I guess leave it for now. So you run that calculation, but instead of this here, you can actually do R, run the function on R, and also just return R in a little vector like that. Then, right, what you can do here is sort by first R's, and then what you do, so that gets you the minimum, and you take second of the first off that list. Is that gonna work? I don't know. Let's see. So we can test that by having something over, excuse me. If I just go under view controls here and add something that's a paragraph, which gives back, if I do calculate hex R, let's give the minimum radius to be, what's a good minimum radius? 1.5 seems pretty good as a minimum. Let's do 1 as a minimum. Minimum radius is 1, and the maximum radius is whatever the user sets here. So let's do 2.5. 2.5. The thickness, we're going to do 0.115. We're just hard coding these to test them out. And the density is 0.285. Does that give me some sensible result, or does it error out? We'll find out here. Wrong number of arguments passed to plate. Okay, so let total mass. Oh, that's right. Yeah, that's a different issue because I changed something. So if I go and have a look at that, that should be property calculations, total mass here. Plate volume is plate, where plate takes add g dash plate R. Right? Okay, next problem. This is where? In what function? Oh, it's in part views here. Plate part view right here. Okay, now we've got something going wrong in the right spot. Crazy thing to say, but that's what I need. Okay, so we've got calculate hex R, wrong number of arguments passed to calculate hex R. Really? Let's open this up. Model logic 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, I messed something up. Min R, max R, T, of course, the mass is what I missed. Let's say I want the mass to be 0.8. Let's see if it can give me a result. Okay, 2.22. Does that make sense? Let's find out. Let's take that and we'll double it. And what I can do here is now calculate the doing it the hard way here. We'll multiply the density times the plate volume of plate taking this radius Okay, that will give us, oops, that should give us the, oh, of course, density right. Okay, so this number here is the closest number. So I asked for 0.8 in the mass, and this was the number that resulted. So if I shrink this step size further to say 0.5, it should get a little closer. Theoretically, yeah, see? So this obviously, so one problem is this does go over in mass, which is actually in the context of, well, one, the degree of accuracy, it doesn't matter, or it's not really possible to get that accurate anyway with how I'm manufacturing this. And two, if you're lifting weights and you expect something to be 5 pounds but it's 5.05, I mean, well, one, that's not going to make any difference, any real difference. And two, if it's heavier than what you think it is, that's not really a bad thing either. It's aligned with the goal of getting stronger. So like if all of the 5 pound weights in every gym in the world were actually 7 pounds, barring any critically tuned in workout regimen, it would be theoretically beneficial to the average person's strength if all the labels were under reporting the weight of something. Anyway, I want to get close to accurate because I like accuracy. Okay, so using the function here, calculate hex radius, and by the way, I am just going to leave this first of all, let me see what it looks like if I do 0.1. That's probably not close enough. Yeah, that's not exactly as close as I want it. I kind of want things to be closer than that. So if I do 0.01 step size, I can get reasonably close. And since I'm kind of brute forcing my way, I'm just checking everything within some range. It seems kind of reasonable to me. So with that, I theoretically I theoretically have everything I need, is what I was thinking, but it isn't true yet. Okay, so the other thing I do need to calculate is plate n. So the number of plates. So there are edge cases where what I'm about to do might break, but I think I can make things work. So okay, so the same idea applies here. I need the desired mass, the density, given the, I want to pass in a plate right away. So that way, plate volume, I just calculate on the plate. Let m plate be plate volume of the plate times the density and yeah, so then I just need the maximum n where the mass is below, where the mass is less than so n minimum is always 2 and n maximum is kind of theoretically unlimited, right? But there's a problem. The reason there's technically a problem here is because as the number of plates increases, the number or the mass of the handle actually increases too. So, right, if I do, oh yeah, I can't control it right now. The reason for that is the total length of the tube that is the handle increases for every n, for every piece that's for every, boy, my brain, where's it at right now? Right, for every plate that's added, the length of the handle piece increases by the thickness of the plate. So what it can do is I could calculate a unit mass unit mass, which is let's change this. Let's do what I want to do, I want the plate end calculation to include the proper increase in mass for the change in length of the handle. And the simple way to do that is I can just add in the mass of a thin slice of a round tube, but I want to know well, let's do it the bad way that I know is easy in my brain. It's not perfect at all, but it's something. So given R and T, what I can do is call plate, which is, I can just call plate with R. Realize I'm making some mistakes, but we're gonna get something working, and then we'll fix it all up. Because what I actually want to do is cut all of this code into its own project, because there's no reason that this should specifically be in the component library. This should be its own project entirely. So that has to come out anyway. And when I refactor it that way, then I can do all the important cleanup and real documentation. So, but this is a good fun hacking starting point. So what I'll do here is make plate be plate R, plate and H is going to be tube round, which is up here, taking R, a T, and an H. And R and T, I happen to know they're kind of hard-coded here. Wait a second, where did I... Oh, that's right here. Tube round is like this. These values are hard-coded because they're not currently exposed to the user, although there's ways that I should make it such. Tube round takes this radius, this thickness, and the height, T. So U mass is multiplying the total volume of a single one, right? The unit mass is going to be add plate volume of P to the property calculations, plate volume, tube volume. Yes, yes, yes. Add tube volume and plate volume, add those together. Oops. Multiply those by the density, and that gives you a unit volume, or pardon me, a unit mass. Then same idea pretty much, right? Well, yeah, let's just use the same logic for now. We do ends for n in range, where the range is a minimum n is 2, and a maximum n we're going to hard code to be 20. Which we can change later. And the step size is 2, because you have to have an even number of plates, because 1 plate for each side. So you always add 2. So for each of those, the mass is going to be, well, yeah, all you do is you just subtract the unit mass, the multiplication unit mass times n from the desired mass. That gets you some difference where you want it to be 0, right? You want the unit mass times n to be as close to 0 as possible without going over. So that's the ends. Now here, you first do is filter by right, so you filter not sure if I'm doing this the smartest way. Let's imagine we'll filter filter negative first. I wonder if this will work the way I expect it to. So 1 1 0 0 negative 1 negative 1. Okay, negative is not, oh, neg. It's not the full word. Okay, that's fine. That's a simple thing to fix. Where'd it go? Hey, it worked. Okay. So using that, oh, it needs to be positive though, right? Yeah, so what you want is filter all the negatives, right? Filter positive first of ends, and then from that I want to follow this here, second first sort by first. Which is confusing, but that's theoretically correct. Okay. Is it gonna work? Let me think about this for a second. Yes, okay, so well, I can follow the same kind of logic here to test this. We'll just make a paragraph here which does calculate plate n given, okay, R is at G plate R, T is at G plate T, mass, desired mass is actually at G, ooh, what did I call it? Globals G desired mass is what it was called. Nice and simple. Desired mass. Okay, so given that should give me some n for some desired mass, and it should grow interesting. Okay. Eight, if that makes sense actually. 14, 18. But if I change the plate R, that number can shift, right? If I make the plate R crazy big, you only need 4 to get the desired mass of 10 pounds. Yeah, okay. So the number, the hard-coded minimum n here should be probably a lot bigger. Let's make it 60. Okay, so using that, we should actually be able to use this, calculate plate n, as a basis for n plates, which would be, so model logic does actually have to go up pretty early into the setup here. Technically above parts, right? It can't be. Can go above all the views though, which is where it'll have to be. Oops. It might have to be. See, it's a little tricky. They're a little interdependent, which is, it's going to be fine, but it's not perfect. If I do here, right, if I let G plate n be equal to this, I don't need it to be in an atom. See if that's true. I might be wrong about that, but I do need to go here and declare I don't think this is correct. We'll find out. Okay, warning. Use of undeclared variable. Okay. G plate n. This might be giving an error because I wonder if atom G plate n Let's see if that fixes it. It does not. Interesting. Well, I shouldn't need it to be in an atom, but let's get this to a state of working again. So we'll comment this one out. We'll put in def g plate n as r/atom, and we'll start with 4. We'll go like that. And that should, okay, it fixes it. Okay, so I need to tie that equation back into this system without causing any loops or anything like that. Oh, it is also, it's faulty. This is wrong. It's a little bit off. So the equation works, but I'm calculating the wrong mass. So I don't want it to be directly the desired mass. I want it to be the desired mass minus the handle mass. Yeah, pretty much. Desired mass minus the handle mass. Yeah. Okay, I'm gonna go to the bathroom for a minute. It's a lot to think about. We're getting somewhere, like we're getting close, which is exciting, but still just out of reach. Oh, something broke? Let's see what's going on here. Okay, that's fine. Desired mass changes that. Rotate is fine. Zoom is fine. Plate T breaks it? Interesting. Why is that? Let's have a look. G plate T. If we go over to parameter view, that should work. Why doesn't it? Well, in just a minute I'll figure it out. I'll try to. Alright, let's try to get to the bottom of this problem. As soon as I touch the plate thickness thing, it goofs up. So let's have a look at the console. Let's get rid of all that. Okay. Cannot compare 0 to some number. Oh. Why can't you? I don't know. Okay, well, I don't get it yet, so I'll try to move on. Get rid of that plate end thing. And let's go right into assembly here. And get rid of the call into plate N here. And instead of this, we do the call into, we do this. And we can produce that up here. N is that whole thing. Oh, PN, plate N. So we do this for N in this range, half of PN. You do that. This should work. Ah, okay, handle, right. Yes, of course. So the handle itself is also incorrect. And we will have to, I think, do a declare, but we'll get there later. So, sorry, no, we'll do it like this. We will declare calculate plate N, because it's used here. And we also want to use that. Oh, I should declare it sooner even. Parts, if we declare it up here, declare calculate plate N. We have handle, let H be something, plate N paste. Oops. Plate N is this big calculation. And here we don't need to call this, we just do PN. That should work. Right, still in design, which is here. It should just be called assembly because that would make more sense. Of course it has to be. I did things in the wrong order. Not a big deal. New line, yes, okay. Instead of at plate n here, we do pn. There's definitely really clever ways to optimize all of this, because this is not very smooth yet. This is not great. pn. Okay, is that everything? Seriously? Total mass. Property calculations. Total mass. Yes. Right, we've got to do pn. Of course. Yes, yes, yes. Delete that. pn. Let's go back up here and copy it because I'm lazy. Copy that from there. Plunk it here. And then here we use pn. Plate n times plate plus handle. Wow, I use this in a lot of spots. That's okay, almost done. Plate n. It looks like things are on the verge of working. Right? We've got 8 is pn calculated down here, and that should change according to the mass. Yep. Okay, that's very good. That's exciting. This should probably still break it. Yes, it does, which we will have to figure out at some point, but luckily not immediately. So now, the next thing I need to do is actually create the total mass calculation, which I'm just gonna do like this. P total mass. Oh, let's do n. Yes, and then here, actual mass is calculated by total mass. Oh, I didn't, it's parameterless, or with no arguments. It's probably not a smart design. So a lot of things I immediately recognize as bad design, which is a nice step in the right direction in terms of mental knowledge about this. Okay, so theoretically, let's also just round this to 3 decimal places for simplicity. A? Why is it like that? That's weird. Oh, no, that's not. Okay. It rounds to 4.6. I got it. Okay, so desired mass. So this is interesting. The actual mass is already over here, and that is related to the error I have where the actual mass is the addition of the plate. No, sorry. The actual mass calculation is correct. The N calculation is actually incorrect because it doesn't currently subtract the mass of the part of the tube that's inside the plates. So what can happen, as happened here I think, is you let N get very close but still under the actual mass, desired mass, but then you're over like the accumulated error of not accounting for the difference because of the tube inside there pushes you over the limit when you should always be at or under. I think that makes sense. Let's try to get a pretty heavy dumbbell. Let's get 50 pounds, 55. Things start to chug, unfortunately, because there's a lot of stuff on screen now. This is the current limit of how I'm doing a lot of things. It's not ideal. It does look pretty neat though. And we're also, like, we're not that far off. I mean, this is arguably a good enough solution, but I don't like it because it's not perfect. Okay, so let's go back down to a desired mass of 5 pounds. Let's let 5 pounds be the minimum that I actually want here, and we'll just kind of work with that for the time being. So I've got this situation here that's quite low from the desired mass, and this is also too big of a plate. So the smallest I can go, see that jumped up quite a bit. That's kind of cool. Let's change the parameter view. Change the plate R slider and allow the step size to be 1/4 inch sizes. This is probably our best bet. Okay, let's see if I can get this number to be just a little more accurate in terms of, let's see if there's stuff I can change. Let's use some model logic. Excuse me. Okay. Oh no, my explanation for why this is wrong also is wrong. Let me think about this for a second. Does n actually equal 12, first of all? Let's zoom in. Let's have a little gander at the side here. 1, 2, 3, 4, 5, 6. Yep, that's good. Okay. Let's split this actual mass calculation into two different calculations as well, just for more clarity. Plate mass, handle mass, single plate mass, all plates mass. Let's leave that. That's good for now. We'll just leave a little separator here for kicks and giggles. Okay, good. I always forget how property calculations, plate volume takes a plate as an argument. Single plate mass, plate volume, where I take plate at G dash plate R. 3 is the rounding value. That seems correct. So I gotta close that. That's the single plate mass. And then all plates mass is just that times N. Which is kind of messy. Ugh. Blech. I don't like it. Okay, we round it, but here we do. I'm really not doing this in like a clean way, which makes me wonder if I should really be stepping back and doing this in a new project file right away. But I kind of don't want to because this is still experimental. I still don't know if this is all the right approach, you know? Okay, so single plate mass, all plates mass. What? Oh, I forgot to multiply. This has to all be multiplied by the density, which is at G dash density. That should bring the plate mass down. Hey? Ah. Okay, there we go. Handle mass is wrong. I did not change the calculation. Okay, so a single plate mass is that. Let me just wait a second, I've got a calculator right here. Let's multiply 1.711 times 8. This is, of course, the volume. I need to multiply this number. That's rounding. Oh, man. multiply this by @g density round. Okay. There we go. That makes more sense. Yeah, so oops. Right, so one plate weighs half a pound almost, so 0.488 pounds times the number of plates estimated is 8 gets us 3.904, which is just a rounding related thing, which is fine. Right, this is probably 7 something. Yeah, and then it rounds, yeah, okay. That's not a big deal. Now handle mass is still incorrect, so what I have to do here is multiply something by the @g-density. Yeah. Right, where something in this case is tube volume, which takes a tube argument, I hope, which should be handle. Okay, 0.7. Yes. Okay, so this number should change as, oop, that was a mistake. Yeah, the handle mass increases because the handle length has increased to accommodate this whole thing. Right, so the mass of all the plates is this. Okay, so here's what I can do to make that closer. What I can do here, I can adjust the desired mass to be I have to do it in here. So I have to let handle mass be times tube volume of handle times @g density. That gets me the handle mass for a particular n, because the handle is always updating when you change n. So wait a second, does that make any sense? I have to change handle now. That's wrong. The handle function handle has to take, oh, this is inconsistent. I need to give handle a n value, where n is the number of plates. Yeah. And then I don't need plate number in here. But I do need, cut that into, yeah, n. Okay, so now handle is dependent on n, which lets me go here. Handle for n is the volume of the tube for that particular n count, which is what I need. And then if I go here, there we go. Right, so now instead of mass, it's actually mass minus handle mass. Yes, that should work. I think that's correct. Which then means I'm thinking myself in circles with the mass calculations a little bit. I think I'm gonna kind of derive it on paper after I'm done streaming, just to make sure I'm actually getting all the numbers right, because there's a reasonable chance that I'm calculating too much up front and then actually subtracting out entire calculations. So I have to really chart it out so that I know what I'm doing, but that is totally fine. Let Pn be this. Oop, that's all wrong. Gotta close that off. There we go. Oop. Let's clean that up a little bit. Just a bit. N now is actually just Pn I mean, really all of these I should put in a let statement, eh? That would make more sense. In fact, if I even make it, this is all so convoluted the way I've done it. I'm not happy with it. I mean, I'm happy in the general sense that it's a working proof of concept, which is pretty cool, but there's a lot more intelligence to be had in terms of the architecture of this, and that's where I'm currently not feeling happy about it. But that's totally fine. It's always a good place to start. Handle is handle Pn. Handle in total mass must take the Pn argument here. And then this one is now in which, that's in the view, assembly view. Isn't it? No, it's in the handle view. Part views, handle view, Pn. Okay. Are we approaching something that makes sense. Okay, that's promising. Oops, that's the wrong slider. This one, rotate, is what I want. Okay, the next thing to fix is this. This looks promising because now I've got the actual mass is less than the desired mass, which makes sense to me. N can get really high, which is not bad, but it's not great either, right? Like, so the plate thickness, I'm currently limited to 0.115. Unfortunately, like I'd like it to be a 1/4 inch steel plate instead. Then you'd have the N of the plates is lower. But I mean, it's not that bad. I'm using scrap for this, so that's why I'm kind of limited to this thickness. See, this is off by 1 pound though, right? Like that's not good enough. But the reason that it's off, if I look at the weight of a single plate here, it's 0.6 pounds. So there's no, if I add 2 plates, which is the only amount that I can add, the actual mass goes over, it overshoots the desired mass. So now what I need to do technically is add, there should be some remaining mass, right? Which should always be less than 2 times the weight of 1 plate. And all I need to do there is calculate the radius of 2 smaller hexes that get kind of bolted on at the end. But before I do that, what I want to do is refresh this so that it's not full of things. I want to zoom in a little bit here. I want to figure out what's going on here. I want to fix that part of my assembly. And if I can manage to fix that, I'll probably be done for the day. Because I've been streaming for about 2 hours, and I feel pretty good about that. Let me see here what's going on. Okay. Okay, this design doc, you know what, actually just, yes, there, okay. Right, assembly, which one of these is the left stack? I gotta see which stack is the one causing the problem. Looks like L stack is the one causing the problem. So what I can do here is Okay, so I've got the length minus the thickness of the plate. It's not just plus the thickness of the plate, is it? Indeed it is. That makes that one easy. Let's check that it still looks correct. No, it's going way off. Why might that be? I don't know. It should just be, it should be length minus, or it should be half the length minus I don't understand. My brain's not thinking. What have I done? Broke it. Okay, we're kind of on the right track here. So it should actually be in each case. Oh man. I mean, I suppose I could do a I wonder. Well, let's try something a little different. Let's do R stack L stack is just going to be R stack f/rotate R stack 180 degrees around Y. What have I done? Oh, yes, of course, this has to be commented out as well. No, this should work. Come on. What did I do wrong? Okay, plate. R stack is this thing. L stack is this thing. Oh yeah, I failed to close the bracket. Okay, sort of. I'm wondering if the problem is not the stack, but is in fact the tube. Oh man, I wonder if it's as simple as this. It is. This is the major downside of hard coding values, right? Is you get spots where if you hard code it twice in two different spots and you change one but not the other, you forget to change it in one spot, and then you end up with weird issues. So that's no good. I'll be right back. Gotta check something. Okay, I'm getting a little tired right now. Kind of think I'm probably gonna wind down for the day. I've fixed that problem, which is of course really nice. There's obviously some improvements to be made with how I'm handling this. It's not very intuitive. There's a lot of things that don't work the way I want, and it's a bit spaghetti-ish in terms, especially in terms of these global defs here. I really should make the part functions pure in the sense that you have to pass in all their parameters instead of having globals that they rely on, because what I can do then is they can be just pure functions, and I could still have globals, but you just pass the globals through the function call instead of just having the function call update the atom. This is bad. This is not really using Clojure's immutable data approach in a smart way. So that's an obvious thing that needs to change. I'm going to change this back to 0, by the way. A few other things I need to do. I need to add diagrams that put dimensions onto front view drawings. So in particular, I need an actual drawing file for this hex shape, and I just need to know the length of the tube to cut, right? Because manufacturing this is actually pretty straightforward. You need the total number of plates to cut. You need a plate template, which is always going to be a hexagon, so you only need to give a few dimensions. The tube size is fixed for this design, so that's always easy. You just need to know the length and the tube type that it is. Oh, of course, I didn't finish this mass thing either. I need diagrams to actually show what plate R actually means. It's the distance from the center of the hex to a corner. So this major radius is what it's called, not the minor radius, not to the side here. It might also be good to have a drawing that shows all possible. So it has the side length, it's got the short R, it's got the long R, and the total. Well, then you don't need the diameters, because then that would be pointless. And then it does need to have the center hole size as well. Easy drawing, then times n, right? Plus 1 times handle length. It's a pretty simple drawing. And then it's just a matter of saying on the drawing, weld together or something. Physical design improvements. This hex plate itself, if I'm welding them together, it might make sense to have on every other face a little notch cut in. That way what you can do is you can align the plates, pinch them in a vise, and then do a weld through the groove. Then it should be all together, and then you just weld through each of the 3 grooves, and it should be good enough. Then you have 2 blocks, and then you just weld them to the ends of the handles on a flat so that the hexes aren't misaligned. Then you can weld those together like I said, and then you can take a grinder and grind everything smooth so there's no hard edges. Grind any flakes off the handle part, and then you can seal it somehow if you want, and just generally clean it up. But for prototypes, keeping it a little rough and tumble isn't such a big deal. Yeah, so that's pretty cool. Next thing to do in terms of actually getting the design change up here is having it calculate the remainder pieces so that you can get even closer to the actual mass. And I just need to link that into the calculation, the model, where am I? The model logic. Yes. Right, so the assembly here, I can have remainder plates, small plate, which is going to be plate, but instead of at G plate R, it has to be S plate for small plate, remainder plate. Small plate is plate, where instead of the plate radius, you use the function calculate hex R. Small plate R is calculate hex R, where you give it the minimum radius of 1, the maximum radius of at G plate R, the thickness at G plate T, the desired mass of remaining mass is going to be half of at G desired mass minus actual mass. Desired mass minus actual mass divided by 2 is the remaining mass, or the half remaining mass technically, but it's fine. So the desired mass here is remaining mass, and then the density is at G density. So that's small plate R. So here plate is small plate R. Yeah, and we'll just leave it f/rotate 0, 90, 0. And let's just see if we add it into here, will it look remotely correct? Small plate. Let's see if that errors out or if it gives us a real result. Not quite. Wonder if small plate R is not calculating properly. Whoops. Let's have a look here. Okay, something's not right. Interesting. I kind of thought this would actually work. Okay, well let's move small plate. It's possible that it just doesn't work at all. Okay. Well, let's actually just return small plate only. It's empty. Does a single plate show up? It should, right? Okay, it does. Okay, so this means what? Let's try a ridiculously small. Oh no, it can't, it has to be at least 1.5, right? Oh no, we can do the smallest radius we can do is I think 0.75. Oh, that's unrealistic technically, but we'll go with it. Okay, plate shows up. Why does small plate not show up? That's my question. What if I just made R mass some big number is just actual mass? Okay, so this won't work because of what reason? I wonder if it's related to maybe actual mass. Well, I don't know what's going on, and that's just gonna have to be something I figure out later. Because this theoretically should produce something, right? It should make some visual of some kind. I mean, it's entirely possible that I'm completely wrong. In fact, it's probable. Yes, warning, each child this. Yes. Oh, is there a way to... first of all, I'll do this. Can clean that part up. Console.log small plate r. No. I'm not sure if this is even the right way to call that. I don't know. Okay, whatever. This is a good enough time for me to. This is a good time for me to stop for the day because I'm not really getting anywhere. I'm just kind of spinning my wheels, testing things without thinking. That's usually an indicator of well, it being a good time to call it for the day. I'll just. Let me just double check that there is a way to get this to work. Oh, wait a second. I can do that in the... Am I being a silly... I think I am. Oh, I'm looking at the wrong thing here. If I, does it work? Okay, it does show up in logs. Hi, yes. Okay, well, let's refresh the page and see if what I want to show up does show up in there. Aish. Okay, here, 1.69 is the radius. Okay, so small plate should work in theory, right? Why not? I don't know. I simply don't know. Small plate. That's gonna fail. Okay, that's going to be it for the day. I shall be back tomorrow. I think what will have happened is a little more work on this, so I have a clearer separation. What I'll do off stream is move all this code into its own project so that it's clean. It's not cluttering up the ASDF namespace, which is still a bad name, and I don't have a better name yet. Maybe I'll come up with that tonight too. But this will be separated out into its own project where I can actually make a good set of notes and have it actually running in a way that is good. In particular, I can build a better design around the globals, as in better state management for those, a smoother construction of the part files and the views, and then a cooler looking document that actually renders out things the way I want efficiently. And I'll keep working on that on the stream tomorrow. So that'll be it for the day. I'm like, as a design goes, I can send this to some people at the shop, and they would be able to, with some dimensions, which are not hard for me to specify, they would be able to make these. So like, it's a workable solution. It's obviously not without its problems, but pardon me, it's a huge step forward for having workable solutions that are kind of interactive. It's really starting to show off the power of what I'm trying to achieve here, at least in my opinion. I'm really happy with it. So I think that was a good day. A little bit of trouble here and there, but that's the way it goes. And yeah, thanks for tuning in. If you're watching this when it's not live, thanks for that, by the way. If you're watching this without a follow or anything like that, it's very helpful if you do follow. If you're watching this on YouTube, it's nice if you subscribe. If you're watching this on Twitch, it's nice if you follow. And if you like the ideas and concepts of programmatic CAD and literate design and programming and just CAD design in general, and you think what I'm doing is an interesting take, consider going to my Patreon and helping me out. Patreon.com/Adam_James. Right here should be good. That's the one, that's me. Let's have a look at the public page. This is what you'd see. Adam James is me, and you can help out on any of these tiers. Give it a think. It would be extremely helpful for me. It would be really good to know that there's some value for other people. It'd be really good. It would help me more easily keep this development up. So consider it if you can. If you can't, that's totally cool too. But I will be signing out for the day. I'll be back again tomorrow. So thanks for tuning in. Thanks for listening at any point, and have a good day.